Hi everyone and welcome back to my channel A in Economist. So in the previous video we have talked about line diagram in detail, and we have also seen a variant of line diagram, that is multiple line diagram. Now in this video we will study what is a ratio chart. So ratio chart is a special kind of a line diagram that shows the relative change in the value of a given variable with respect to the change in time. So ratio chart is a special case of line diagram, and it shows the relative change instead of absolute change. It focuses on the relative change of the value of a given variable with respect to the change in time. So what is the special feature of this chart? The special feature is the horizontal scale is arithmetic or natural in nature. So the scale that you usually use is the arithmetic scale or the natural scale, and the horizontal axis of this diagram uses that scale only, but the vertical scale is logarithmic. So you are basically plotting, here you have the normal scale, but here you have, suppose this is x here. On the y-axis, what you have to do, you have to take the log x, the ln x or the logarithmic scale for that variable, and hence it is called the semi-logarithmic chart, right? It is called the semi-logarithmic chart because on one axis, particularly in the vertical axis, you are using the log scale, but on the horizontal axis you are using the natural arithmetic scale. Now ratio chart enables one to exhibit chronological data having large difference in the values of a variable under study. So when this chart will be useful? This chart will be useful when the range of values on the y-axis is very large and it is very difficult for you to fit the values using an arithmetic or natural scale. And we will show this with the help of an example. Let's see this example of a ratio chart. It says bacterial growth in the medium over the course of weeks. So the first diagram shows the regular graph. If you take natural scale for both the axes, on the x-axis you have weeks, which is 1, 2, 3, 4, 5. So this study spans over 5 weeks, and you are plotting it in natural scale. On the vertical axis you have the cell count or the bacterial growth in over these 5 weeks, right? And this vertical axis is also measured in natural scale. Now what do you see here? The cell count ranges from 0, starting from 0, it spans over a lakh. Now if you plot 0 to 1 lakh cell count on this vertical axis, it will give you a diagram like this, which is very not giving you meaningful insights because it is very messy in nature. Why this is so? Because if you see from the first week to almost the third week, you don't have any cell count, or you have a cell count which is very insignificant, and you can't see this in natural eye, right? It almost coincides with the vertical axis. If you can see the blue line, you will see that the cell count are too low that it almost merges with the horizontal axis, and you are not getting any significant result from here. Now from the third to fourth week, within 1 week, you have a little increment in the bacterial count, and it will be somewhere around here, right? So still the bacterial count is very low, what we see from our natural naked eye, right? So here you can't see any significant increment also. Increment is very less. Now from fourth week to fifth week, you'll see a drastic change in the bacterial count. So from the first to fourth week, the cell count is very low, or low. If we take the scale to be like this, from 0 to 25,000, if you measure 1 centimeter equals to 25,000 cells, then you will feel that it is very low, but actually may not be. It's very low, right? So 25k is a large number of cell, right? But if you plot this using natural scale, it will seem to you that the cell count is very low, or it is not growing at all, right? So it will give you misleading conclusions. If you use this kind of scale for both the axes, it will give you misleading conclusion, right? So to avoid this problem, if you want to make a more meaningful graph, what you have to do, you are not changing the horizontal axis. It is as it is. It spans over 5 weeks. But now you are using a different scale of value for the vertical axis. Here you are taking logarithmic scale. Here you are taking logarithmic scale to measure the bacterial growth in the medium. And in the same graph, if you draw using this ratio chart, this will give you a smooth graph. So you will see that from the first week to fifth week, you have a significant growth. You have a continuous growth or a significant growth in the bacterial count if you measure the cell count like this. First you have 10, then you have 100, then you have 1000, then you have 10,000, then you have a lakh. And why this is so? So basically variables with higher range of values can be visually presented in a better way using the ratio chart. And to know the reasoning better, I have given you this paragraph. I found it on the internet, and I found the explanation to be very suitable for this. I have given you a screenshot of that site, and you can pause the video, you can read it on your own, but I want you to particularly show this highlighted part where it says that when the y-axis of a semi-logarithmic plot is logarithmically scaled, data or functions that demonstrate exponential characteristics will appear to be linear, right? Appear to be linear. So that is exactly what you have seen here, that if you consider both the natural scale, then it is almost like this, and then it grows gradually significantly from fourth week onwards. But if you convert one vertical scale to be logarithmic in nature, then you have a smooth linear graph, which is more meaningful for your study. So it basically demonstrates the exponential characteristics to be linear. This is so because logarithmic scale compresses the larger values, making them more visible and easier to compare to smaller values. The linear scale on the x-axis keeps the value on the x-axis in the same proportion, making it easier to compare the slope of the data. So this is the reasoning, that logarithmic scale compresses the larger values, making them more visible and easier to compare to the smaller values. I hope this is understood. This is the benefit of using logarithmic scale for one axis, right? And you might think that to use this for economic purposes, right? So you can think of an example of the stock market, right? In the stock market, what happens is that if you see in the stock market prices, if you follow stock market price, then you'll see that it does not have a particular trend. So it will, for every second it has a has a significant fluctuation. Sometimes it is lower, sometimes it is getting higher, sometimes it is getting constant level. So when stock prices has a higher range of values, right, it can vary significantly each second. And to measure that kind of changes, stock price, if it goes up significantly or goes down significantly, then this logarithmic chart will be a better option for you to depict that variation or depict that change, right? So stock market will be a good example from the economic or from the finance point of view if you want to know the application of ratio chart. This is where economists also use the ratio chart to depict this phenomena. And there could be other examples as well. You can pause the video and take a look at this. Here you have some other examples, right? Okay. Next up, what we have is the bar diagram. What is a bar diagram? It comprises of a number of equidistant rectangles. Bar diagram, you have equidistant rectangles which is termed as bars, each of them being meant for some specific category of the available data. We will see this also with the help of example, but bars is of common width which is conveniently chosen are drawn to the base of the line, the length or the height representing the value corresponding to each category. We will see this in a while. And bar diagrams can be both vertical and horizontal, where vertical bars are usually drawn for time series data. So when you have time on one axis and variable under concern on the y axis, then vertical bar diagram is more appropriate. And horizontal, you use horizontal bar diagram for spatial data. What is spatial data? Spatial means the data which is related to geographical location. We will see examples of this also. So data which is related to geographical location falls under the category of spatial data, and horizontal bar diagram is a better way of representing spatial data. Now look at this example of simple bar diagram. Bar diagram of favorite sport of students, right? So you have 5 categories here. On the x-axis you put the categories, types of sports. What are the categories? You have golf, you have tennis, you have football, you have rugby, and you have basketball. And for each of the category you are drawing a separate bar diagram, where the height, this particular height of each of the bar represent the value that this category has, represents, right? For golf, the suppose this value is 6, so the height of the bar represents the value 6, that is 6 students prefer golf over every other sport, right? For tennis, this number is might be 8, so 8 students, this height represent 8 students prefer tennis over all the other sports, and similarly for football, for rugby, for basketball. So that is why I have written here that height, the length or the height of the bar represents the value of the corresponding category. This is the significance, or this is the essence of a bar diagram. And here you have to mention the scale, that 1 unit is 5 students. Here on the horizontal axis you have equidistant bars, so here scale is not that important because you are giving some distance, equidistance between each of the bar. So for the horizontal axis you may not mention the scale, but for the vertical axis you have to mention that 1 unit or 1 centimeter. If you draw it on your copy, it will be representing 5 students here, right? This is the simple bar diagram, and it is vertical bar diagram. The bars are drawn vertically, right? Now this is an example of horizontal bar diagram, where what you see is that here you have number of students on the horizontal axis, where 1 centimeter represents 10 students, right? 1 centimeter represents 10 students, and on the horizontal axis you have different subjects. So for the particular category subject music, the length of the bar, this is the length of the bar, it represents 90 students, right? So 90 students have passed in the category music as a subject. Similarly, you can do this for every subject. You have maths, history, science. So for maths you have 40 students that have passed maths, and for history you have 80 students who have passed history, right? So in this way you can derive conclusions for this horizontal bar diagram. For each category, the essence of the bar diagram is the same, that for each category the length of the bars will give you the corresponding number or the value that the bar represents. For each category you are drawing a single bar, and the distance will be the same, equidistant bars. For our convenience we draw this equidistant manner. Now what I was telling you is the spatial data. This is an example of spatial a bar diagram which represents the spatial data because it relates to the state. If you can see this, it is the state, American states. Here you have few American states, and for each state you are trying to derive the profit. You are trying to compare the profits of each of the state. So you can derive what you can the conclusion you can derive from here is that California records the highest profit, and the profitability is around 600k for them. And second place you have Washington has 250k profit, and on the third place you have Colorado, which records around 80k profit. So from this bar itself you can compare between the profits of different states. Also you can rank them. Also you can see which states are performing poorly, which has close to 0k profits, right? So this is the bar diagram representing spatial data because it relates to geographical locations. When you are comparing between states or comparing between countries or continents, this will be the bar diagram representing spatial data which relates to geographical location. And next we have multiple bar diagram and divided bar diagram. These are variants of bar diagram, but I don't want to make this video longer than this. We'll know this in the next lecture. Stay tuned for the next lecture, and thank you for your time. If you have any doubts, let me know in the comment section. Thank you for your time.